Thank you. So my name is Panagiotis Vekris, and this is a joint work with Ben Cosman and Ranjit Jhala from UC San Diego. The title of this work is Trust by Verify, and this is a two-phase typing technique for dynamic languages. And even though this is the gradual typing session, this technique is purely static. So the main focus of this work are on scripting languages. And when scripting languages were first conceived, their main goal was to glue application modules that were usually written and compiled from other languages that are so-called like system programming languages. So their design was mostly typeless, and that had its merit since it allowed developers to have a more rapid development and deployment of their code. However, nowadays, a great deal of applications like full stack are written in scripting languages, for example, JavaScript and so on, and not just the front ends, but also server-side applications. And so developers more and more figure out that the support that they can get from tooling, such as typing support from TypeScript or Flow type, it gets really good results for them. But as applications become more and more complex and reasoning about them is a complicated process, this calls for stronger guarantees. And this is exactly the purpose of this talk, namely like static verification of scripting languages. And to make this goal more concrete, let's look at a simple example and assume that we are called to write a program that just computes the index of the smallest element of an array. But with an important restriction that we need to verify that all array accesses are within bounds. So when first order program that solves this problem is, for example, the following, like a function minIndex FO that defines a variable rest that will hold the result. It gets initialized to 0 and gets returned at the end of the function block. It does an iteration over the elements of the array. And at the core of this iterating process, it checks that if the current element is smaller than the so far found minimum element of the array. And if necessary, it does the necessary update. And we also include a sanity check on the length of the array. So back to our original goal. Checking array bounds in this example, we claim it's easy because we can use a data flow analysis to establish an ordering on the values that res or I in the length of the array is. And so we can prove our target very easily. However, nowadays, there's a common idiom among developers to abstract some operations. And in particular, we see here the function called $reduce that does the same iterating process over the array, but abstracts over the what's happening inside the body of the loop. So in this case, we can actually implement a minIndex HO that does the same thing as before. The goal is the same, but calls $reduce with a step function that it defines itself and passes to the reduce function and an initializer as well. And our main claim here is that in order to prove that array bounds, in order to prove that the array accesses are correct in this program, one needs to reason about relational facts among values and closures. And our claim is that it's hard to do this with data flow analyses. Instead, what we propose in this work is to use refinement types, which we claim that offers us an easier way to track these relational facts. So this is going to be the main approach for this talk. And let's see what exactly we mean by refinement types through a simple example. So this is let's assume that we want to define a type index of A, which will be the set of valid indices for an array A. And this is what it will look like. In particular, there will be a base type part. In this case, this is a number, and a logical predicate type associated with the base type. We also notice that there's a value variable v to denote the element of the set that we're describing in particular. And we can see that this is a valid description of what we actually want to say here, in that v is greater or equal than 0, which is the case for indices, and also is bound by the length of the array A. So back to our higher order reduce example. Assume we want to use these types to type this to give a signature to this function. One first step we need to take is to assign some base typing. In particular, here we're using TypeScript form. So this is what a signature of this function would look like in TypeScript. And then we can apply the definition that we had earlier for the index type on top of this base type. In particular, the part that's going to change is the third argument of the f function argument, which will denote now that that argument is a valid indexer for the array A, which is the first argument of reduce. So the forward refinement types that we used, one of the first works that introduced them was that by Z and Penig back in '99. And one of the main prerequisites for these refinements is that the language possesses an unrefined static type system that provides some basic invariants about values. So we depict this dependency with this graph where value analysis basically refers to what the refinement types are there for, and type analysis is basically the base type system. And in the case for scripting languages, there's another interesting situation that arises very commonly. In particular, if we look at the JavaScript API for array reduce, we'll notice that the second argument for reduce is in fact an optional argument. So this situation is what we will call value-based overloading, and this is going to be the main problem that we're trying to tackle in this work. But let's take a closer look to see the intuition behind this notion. So here's a potential implementation for the reduce function. And what it does is that it dynamically reflects on the number of arguments that are passed to reduce through the intrinsic JavaScript arguments variable. And it proceeds differently in each case of the conditional. In particular, when it's typed, when called with 3 values, this is what the type looks like. Whereas called with 2 values, it has a different type that doesn't account for the last argument. And so what we realize here is that in order to reason about the base types themselves, we also need to add an extra, to also reason about values that flow through the program. And so in addition to the dependency from value analysis on type analysis, there's also a dependency from type analysis, like basic types, onto values. Because we must reason about this logical relationship between values, which incidentally is the problem that we wish to solve for in the first place using refinement types. So as we can see, this causes a circular dependency, which makes reasoning about these programs a little more awkward. And so this is exactly the problem that our two-phase typing approach tries to solve. So moving forward, let's look at the main intuition behind this approach. So first of all, let's see what the high-level goal is here. And to do this, we'll introduce an even simpler program called negate that takes 2 arguments, a flag and x. And the developer's idea here is that if flag is non-zero, then x really needs to be a number so that it will fall under the first branch of the conditional. Otherwise, if flag is 0, then it is supposed to be Boolean. So there is this invariant that needs to hold. So in this sense, these first two calls to negate should be correct, with 1, 1, and 0 true, whereas these two last calls to negate should be deemed as false by our checker. So moving on, let's see how we can actually describe this intuition through a specification and using the refinement types that we talked about earlier. In particular, let's see a couple of extra definitions for truthy types and falsy types. These are basically numeric types whose values is non-zero in the first case and 0 in the second one. And now the intuition that we described earlier can be encoded as if the flag has a truthy type, then x is in fact a number. Otherwise, if it's falsy, then x needs to be Boolean. And we can actually incorporate this intuition in negate's type into an overloaded signature for negate. And the goal of this approach is to actually verify that the body of negate actually fulfills the promise stated in the specification, and also that call sites actually check against the specification for negate. So moving on, this is a high-level bit of the tool workflow. So the input of our technique is going to be a source program with specifications that have the form that we saw earlier. As we said, this is a two-phase typing approach, and the output is basically a yes or no that says that the source program, in fact, satisfies the specification or not. And the two parts of the approach are called trust and verify, each containing several sub-steps. The output of the trust phase is an elaborated program that we'll describe soon. And the verify phase also has some steps itself. So we'll start off with the first step of the trust phase, which is the cloning. And the main thing we do here is split the overloaded functions such that each one of the two clones has one of the two conjuncts of the original overloaded signature. So the first case will get the flag truthy, and the second one the flag falsy with number and Boolean respectively. Moving on to the cast phase. This is basically checking for each one of the clones separately to guarantee that they actually satisfy their assigned signature. Let's focus on one of the two since they're pretty similar and their ideas are pretty similar. One thing we need to mention here is that this phase is agnostic to the refinement part, the logical predicate that we showed earlier. So we can replace the TT type that we had before with just number, which is the base type. And then we proceed with a path and value insensitive checking approach, which is similar to something like that TypeScript, for example, would do, or perhaps other type checking techniques for similar programs. But what we'll realize is that TypeScript will probably not allow this program to type check. And the reason is that we're trying to apply a numeric variable to a Boolean operation, and so we'll reject this program. On the contrary, we will not reject this program, but instead we're going to wrap the erroneous expression, in this case the x, the variable x, into a dead cast. Dead cast can be thought of as a function that has the signature shown in the middle here. And intuitively, it's similar to an assert false, but also returns a type B that can be anything that we actually need to have at that spot. Basically, this means that this code needs to be dead code. We do similarly for the other clone that we had earlier, but assign the dead cast in the other branch. And then move on to the last part of the trust phase, which is the overload resolution. In particular, how do we figure out which overload to use for each one of the call sites? So for the first case, the main idea here is that we proceed in resolving based on just the base types. So here, the second argument is the one that differs, so that's going to be the one that's going to determine the resolution. And so for the first case, we realize that it's the first argument, is the first signature. Same holds for the third signature, for the third call to negate. And in a very similar manner, the second and fourth are assigned to the second signature. So following on these first two steps, we have come up with an elaborated program that is fed to the verify part of the approach. So the first part of the verification is generating constraints for both each clone of negate that we have so far, and also the call sites. So if we check the first case, we're going to have to, the refinement typing in this case is going to be a flow and path sensitive technique. So we're going to have to keep track of an environment and a set of guards that actually account for path sensitivity. We start off by adding flag in X to the environment. And for the first branch of the conditional, we assign a flag not equal to 0. And in the second one, that's actually of more interest to us, we assign flag equal to 0. And then carry on with the deadcast expression. So this is a function. This is treated as a function call. So we'll have to add a subtyping constraint between the type of the argument that we pass to the deadcast and the type of the argument that deadcast expects. And so in this case, X has type number such that V equals X. And the right-hand side is just false in this case. And finally, we produce a verification condition, which is basically the construction of a logical implication based on the above subtyping constraint. This has to take into account the environment and the guards that we've seen so far, and also the left-hand side and the right-hand side of the subtyping constraint. So if we want to populate this implication, we first add the first part of the environment with the necessary substitutions. Now the second part doesn't, X doesn't have a logical predicate, so a trivial true is implied in this case. We also add the flag equal to 0, the guard. And then moving on, we need to make sure that the base types for the two sides of the subtyping constraints are the same, but this is actually guaranteed by this approach, by our elaboration process. So after this, so at this step, we just add V equals X as the left-hand side and false as the right-hand side. So moving on to the constraint generation for the call sites. This is also straightforward. We're just going to see the case for the first, for the calls to just negate #1, so for the first clone to negate. In particular, OK1 and variable is OK1 and bad1. So in this case, we are calling negate1 with 1 and 1. So the so we're going to have two subtyping constraints, one for each argument. The first one is going to be that number that is equal to 1 is a subtype of a number that such that V is not 0, which is what TT expands to. Similarly for the second constraint, for the second argument. And we repeat the same thing for the bad case, for the bad1 variable. In a very similar manner to before, we're going to create our logical implications from these subtyping constraints. So moving up to the checking phase, we are going to gather the logical implications that we've seen so far. Perhaps this program has more, but just for the purposes of this demonstration, we're just going to see these ones. So basically, we have the one from the gates body and the two for the call site. And then we feed this to an SMT solver to basically tell us if these are actually correct or not. So the first implication is correct because there is an inconsistency. There was an inconsistency in the environment, which basically adds up to basically having dead code at that point. The first, second, and fourth lines of the remaining constraints are actually satisfied, are trivially correct. And the third one is wrong, which is something that we expected, because we expect this call to go wrong, actually. So this concludes the description of the approach, and I just want to have go over some of the benefits over previous work, since there has been quite a few work on this area of typing for scripting languages. In particular, one benefit is that we can have very expressive specification due to the use of complex value relationships in the refinement logic that we use. This is to be compared to techniques like occurrence typing, such as inflow typing and typed racket that we've seen earlier, where they were more restricted in a fixed set of type tests. This technique also allows for automated verification in that composing simple type checkers with program logics allows us to use techniques like abstract interpretation to give us inference for the refinements and hence lower the annotation burden for the developer. And this is to be compared to approaches like dependent JavaScript and so on. And finally, our semantics preserving elaboration allows us to have establish end-to-end soundness, and this is one point that I'm going to go into a little more detail, which is the formal result of our work. In particular, the source language of our elaboration is a lambda calculus with intersections and untagged unions to denote the value-based overloading. And our base type checking is basically an assignment of a type A to this expression E. And then we have an elaboration of expression E to an expression M of our target language that doesn't have value-based overloading, but instead has products, tag unions, and deadcast, as we saw earlier. And this elaboration is largely attributed to a work done in 2012 by Dunfield. And so let's take a look at one of the results that we have established to that, which is that if we type expression E with a type A and elaborate it to an expression M, then after some number of steps in each side of the elaboration, then we will also be able to get some relation between the expression E prime and M prime. And this is to show that elaboration preserves the semantics of the original program. In this slide, I'm glossing over some of the details of what these stars actually mean. In the paper, there are more precise definitions of how many steps are done in each side. And then finally, as part of our end-to-end type safety theorem, if we are able to establish both that E is type checks in the elaboration phase and gets elaborated to an expression M, and we can also check M with a refinement type checker, the verify stage, then we get type safety in that E will not crash. So finally, this is as part of our future work, we're trying to use this approach as a foundation for refinement type checker for TypeScript, and we're working on getting a lot of the object-oriented programming features in our code, and in particular things like imperative features and objects and mutation, and this is a snapshot of what it looks like for the example that we saw earlier. And with this, I would like to conclude, and thank you.
Any questions? So thanks, this is very cool. You're turning statements about types entirely into true when you're translating them into SMT formulas. So that seems like it's going to be a little less expressive than in, say, the nested refinements work, where type of tests do go to the SMT solver. Is that accurate?
Well, yes. I mean, our approach, the refinement type language that we have is not as expressive than as DJS in that we can't have nested refinements. So all the type structure needs to be encoded in the base type system.
Hi, so you mentioned TypeScript a few times, and I'm curious, did you also run your examples through Flow?
We have not run examples through Flow. We're
Okay.
using TypeScript as our front end to do some parsing and get some basic typing. But then we actually...
Okay. So the reason I ask is that Flow has some basic refinements built in. It does like reasoning with singleton types and equality checks among them and so on. So obviously your technique is far more general, but it also uses these two-phase things, whereas Flow managed to do this in one phase. So I'm wondering if you have done any kind of evaluation on where this additional relational kind of properties arise in practice in JavaScript that would really use your technique versus like do fine with simpler things. I'm just asking because we would want to add these things to Flow as well.
Right. So I have one example where which might be interesting, and this was in the TypeScript compiler itself that we have as part of our code base that we've run already, where some of the tag tests to narrow down some type were based on basically bit vectors, and reasoning about those would require some masking and some bit vector operations that wasn't really quite straightforward how to do without actually using more appropriate logics that our refinements allow.
Should be handled fine by Flow as well, and also the optional value thing that you showed at the beginning of the talk. ES6 now has optional properties. So all you need to do is like rather than checking the length of arguments, you would typically check whether some parameter is undefined or not. So again, I mean,
I see.
Any other questions?